I would like to solve this example that talks about writing the sample space for different experiments. Consider two games, both involving 7 successive coin tosses. Write the sample space for each game. Game 1. We receive $1 each time a head comes up. Okay. Game 2. We receive $1 for every coin toss up to and including the first time a head comes up. Then we receive $2 for every coin toss up to and including the second time a head comes up. So basically, the dollar amount per toss is doubled each time a head comes up. Look at the game 1. We receive $1 each time a head comes up. So we have 7 successive coin tosses. As an example, we get something like this: tail, head, tail, tail, head, tail, head. Okay? So we get $1 for this head, $1 for this one, and $1 for this one. So together I get $3 because I get 3 heads in this coin toss. And so as you see in game 1, the total number of heads is important. Okay, and so the sample space here would be the number of times that we get head. I get 0 head when I get tail, 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 and tail for the 7 successive coin toss. Or I get 1 head, 2 heads, or up to 7 heads. Okay, so the sample space here would be just the total number of heads. But look at game 2. On game 2, we receive $1 for every coin toss up to and including the first time a head comes up. Then we get $2. Okay, then we go to $4 every time it gets doubled. Okay, so look at the same result: tail, head, tail, tail, head, tail, head. Okay, so how much money we get if we have this result? We receive $1 for every coin toss up to and including the first time that we get head. Then we get $2. So I get $2 in here, $2 in here, and $2 in here. Then it gets doubled. Then I get $4 and $4. Okay, so as you see in game 2, the order of heads and tail is also important. So in game 2, the order of heads and tails is important. Because if we get different result, some other results like this, head, tail, 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 head, head, tail. If we get something like that, I get $1 in here. Then I get 2, 2, 2, 2. Then I get 3. And then I get 4. So, oh, I'm sorry. Not 3. Then, so this would be the 3rd time that I have head. So it would be 4. And then I go to the next one. So it would be $8. So you see the amount of money would be so much different between these 2 results. So since the order here is important, when I want to write the sample space, I need to consider all different results for the 7 successive coin tosses. I need to write when I get all of them tail, or when I get all of them heads, then I get tail, head, head, tail, tail, head, for example. And I need to write all different results for the 7 successive coin tosses, and the number of all the outcomes that are considered in my sample space in here would be 2 to the 7th because I have 7 spots or 7 results, and in each result I have 2 options, head and tails. So together I get 2 to the power of 7 as the number of elements that I have in my sample space in here. But in the game 1, since just the total number of heads is important, I can get 0 head or up to 7 heads. Let's talk about probability axioms. If we have a sample space omega, and the sample space is the set consisting of all the outcomes of an experiment, then an event A would be any subset of the sample space. By the first axiom, we say that probability of any event is greater than or equal to 0. Probability of the sample space is 1, and if we have 2 disjoint events, then probability of their union is the summation of their probabilities. Let's see how to construct a probability law starting from common sense assumptions about the model. Okay, the first one is a single coin toss. In that case, if we have a coin and we toss it, the sample space would be just head and tails. H is for heads and T is for tails. What are the events? Events are basically any subset of the sample space. So events, so they can be head, tail. The whole sample space is also a subset, and empty space. So we have 4 events here. Now we assume that we have a fair coin, which means what? Which means that heads and tails are equally likely. Which means that probability of getting head is exactly equal to probability of getting tail. Okay, that's the outcomes of a fair coin. Okay, so now look at the probability of the sample space. By the second axiom, probability of the sample space is 1. And by the third axiom is the summation of probabilities of heads and tails. So it would be probability of heads plus probability of tail. Okay, now since probability of head and tail are equal to each other, this one is equal to that one. So I can replace probability of tail with probability of heads. So I get 2 probability of heads. Therefore, probability of heads is equal to, so you see 1 is equal to 2 probability of heads. So probability of heads is 1/2. So see what we got. We got probability of head equals to 1/2, and it's also equal to probability of tails because we have a fair coin. Probability of the sample space is 1. How about probability of empty space? So one of the outcomes for sure is going to happen because we have a fair coin. So we get heads or tail if we just toss the coin. Therefore, we say that probability of getting empty is 0 because at least we get one of the outcomes. So this is a probability law that satisfies, let me just write it. So this is the probability law that satisfies all these 3 axioms, and we just got it by the common sense. How about the second experiment? On the second experiment, we have 3 coin tosses. Okay, If we have a 3 coin tosses, the sample space is what? For example, on the first one we get head, on the second coin toss we get head, on the third one we get head. Or we might get head on the first one, head on the second one, tail on the third one. Or we get head, tail, head, head, tail, tail. We get tail, head, head, tail, head, tail, 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 head, and tail, tail, tail. So we have 8 possible outcomes. This is our sample space. Now, events is since we have fair coins, events would be any subset of omega. Just assume, for example, just take one of them. A would be if we get exactly 2 heads. Okay. 2 head means what? We get head, head, tail. We get head, tail, head. And we get tail, head, head. Okay, so this is A. Now let's just talk about probability of A to see what we got. So probability of A, which is head, 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 tail, head, 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 tail, and tail, head, head. Okay, we would like to see what is this probability of A. Okay, so what is that? It's by the third axiom is the summation of each one of them. Head, head, tail. Okay, and now what is probability of each one? If we just copy whatever that we did in here on the first experiment with a single coin toss, we say that since we have fair coins in here, probability of the sample space is 1, which would be the addition of probability of each one of the outcomes, and we get 8 of them, so probability of each one of them would be 1/8. So I have 1/8 in here, 1/8 for the probability of head, tail, head, and 1/8 for the probability of the last one. So we get 3 times 1/8. So 3/8. As you see, the law that we got in here, if you do the same thing for all the events, all the subsets of omega, we see that this probability law says that for any event is equal to 1/8 times the number of possible outcomes contained in this event. This probability law that we got in here, let me just write it. Okay, this probability law that we got satisfies all 3 axioms. So we use common sense to find probability law for these 2 experiments. In this example, we're going to study a continuous model, and we're going to see how to apply probability axioms to find a probability law for this question. Romeo and Juliet have a date at a given time. Each will arrive at the meeting place with a delay between 0 and an hour. All pairs of delays are equally likely. The first to arrive will wait for 15 minutes and will leave if the other has not yet arrived. What is the probability that they will meet each other? Okay, so it says that each of them have a delay between 0 and an hour. So I can have the sample space as 1 square. X would be the delay for Romeo, and Y is the delay for Juliet. And they have a delay between 0 and an hour, so I have a square in here. Let me make it better. Okay, and as you see, each pair in here, each point in here is a pair. The first coordinate would be the delay for Romeo, and the second coordinate would be the delay for Juliet. Okay, and it says that all pairs of delays are equally likely. What it means that we can write the probability of our sample space to be the area of the square, of this square. Okay. And in that case, I can say that any event, basically what is the event? Since this is our sample space, any event would be any subset in here consisting of all the points. Each point is a pair with a delay for each one of them. And probability of any event is the area of the event. Area of the event. Okay, now is this probability law good? Let's check the axioms. Okay, so what are the axioms? Probability of the event should be positive. Area here is the probability, and its area is positive, so 1 is checked. Probability of the sample space is 1. It's just because the probability of the sample space would be the area of the sample space, and we have a square of size 1. Every side is 1, so the area of the sample space is 1. And if we have two disjoint events like this, A and B, probability of their union would be the area of their union, which would be the summation of the area of each one of them. So as you see that this probability law that we define in here, based on our continuous model, satisfies all three axioms. So that's good. Okay, so now we want to see what is the probability that they will meet each other. So if the first one arrives, he or she is gonna wait for 15 minutes, and if the other one has not arrived, it's gonna leave, or she's gonna leave. So the differences between their delays should be less than 15 minutes if they want to meet each other. So let me write in here, I'm gonna say that let M be the event that they meet, which means what? Which means that their delays, the delay for the Romeo and for the Juliet, should be in such a case that the difference between delays is less than 15 minutes. 15 minutes in that case, because this is time between 0 and hour, would be 1/4. Okay, and I know that X, the delay time for the Romeo is between 0 and hour, and Y delay for the second for Juliet is between 0 and hour. Perfect. So let me try to graph M in here. We're gonna go back to calculus. What do I have in here? I have the absolute value of X minus Y less than 1/4. So X minus Y is less than 1/4, and X minus Y is bigger than -1/4. Okay, so I have these two inequalities based on the absolute value inequality that I have in here. Let me try to graph this one. Again, back to calculus. When we want to graph inequality, first we need to graph equality of that. So this is a line. Let me give it some points. So if Y is 0, I'm gonna plug in Y is 0, X is 1/4. If X is 1, I'm gonna have 1 in here, negative y goes to the other side, 1/4 goes in here, so y is 3/4. So I have the points 1, 3/4, and 1/4 and 0. So 1, 3/4, and 1/4 this. So the line would be this line. Okay, actually let me kind of continue that. This is the line x minus y equals to 1/4. Okay, now that I have inequality, I need to see which area is this inequality. Is this the area below this line? Is this the area along on the line, or this is the area above the line? Okay, so to just find out which area is this inequality, I just need to pick a point. I'm gonna pick this point in here, 0, 1. I'm gonna plug in 0, 1 into here, the point 0, 1. So x is 0, y is 1, so negative 1 is less than 1/4. Check. Therefore, all the areas here would be my inequality. Okay, let me erase these ones just to clean up a little. Okay, so remember that this part above this line is the area for this inequality. We can do the same thing for that one. Let me just make it a little fast. So 1/4 is x minus y. I'm gonna have x and y when x is 0, y is 1/4. When y is 1, x is 3/4. So 0, 1/4, this one, and x is 3/4, y is 1. Okay. Great. And you're gonna check again. So this line in here is x minus y equals to negative 1/4. So I'm gonna pick a point, like I'm gonna choose one point in here, 1 and 0. So 1 minus 0, is it bigger than negative 1/4? Yes. So the area below this line would be the area that I'm looking for. Okay, oops. So this is the region M that I was looking for. Now to find probability of M, which is the area of M, because this is the event M that I'm looking for, which would be the area. The probability of that would be the area. So to find the area in here, it's better to consider the area of the whole square and subtract the area of these two triangles. Okay, so what is the area here? So the area here would be the length of the base, 3/4, times the height is 3/4, times 1/2. So this is 9/32. And this is the same thing in here. The area is 9/32. So now the area of M would be 1 minus 2 times 9/32, which is 1 minus 9/16, which is 7/16. Okay, so 7/16 is the probability that they meet each other because the difference between their delays is less than 15 minutes on 1/4.